It's my great pleasure to introduce Iair Arcavi for this last of the summer talks. He got his PhD in 2013 from the Weizmann Institute in Israel. He then went on to the University of California, Santa Barbara. He was an Einstein Fellow, which means he's very smart. And then after that, he's now become faculty at Tel Aviv University, which is great because he was an undergraduate at Tel Aviv as well, which is always nice to be faculty at the same place where your old professors who taught you introductory courses are also there. Iair is an accomplished public speaker. He's been particularly involved in something called Astronomy on Tap, which maybe has not established itself yet in Aspen, but has many public talk series across the country. In particular, Iair was very involved in the chapter in Santa Barbara. He was also, of course, involved in this incredible discovery. And it's just an amazing story. If you're a real science buff and you want to hear about these like eureka moments, this is a true eureka moment. Unfortunately, Iair chose his title a little incorrectly for this particular town, turning stars into gold. Here we are in Aspen. What he may or may not mention is that he's also figured out the way to turn stars into silver, which of course, here in Aspen we really appreciate. So with that, Iair, please take it away. And at the end, we'll have some time for questions. So thank you all for coming.
Yes, I'm very excited to be here in Aspen and to tell you this amazing story that I think many of us as scientists kind of can only hope for to have maybe once in our career something like this. But this is really just the beginning of something huge that is happening in the field, and we are in an extremely fortunate time to be witnessing it, and even more privileged to be taking a part of it. Okay, so what is the story? Well, the story starts 130 million years ago in a distant galaxy where two neutron stars were orbiting each other, and as they did so, they were generating disturbances in space-time, and that caused them to merge and produce this burst of gravitational waves, light, and heavy elements and matter across the universe. Now, the gravitational waves and the light traveled across the universe. Let's get this working. Okay. Traveled for 130 million years across the universe until on the early morning hours of August 17th, 2017, they reached planet Earth. And for the first time in the history of planet Earth, we had the technology to detect those waves as they arrived. So this was the first time ever that we detected gravitational waves and light from the same event. And this is a very big deal because for 400 years, ever since the invention of the telescope, and even before that, almost everything we know about the universe has come from light that has come to us from these distant objects. Okay, so astronomers, we feel kind of like prisoners here on planet Earth. We cannot go out and study the things that interest us. We need to have these messengers come and tell us about them. And the almost only messenger we had for the last 400 years and forever has been light. And 4 years ago, that changed when we were able to detect gravitational waves for the first time. And this is a completely different type of messenger that can tell us things about the universe that light doesn't know about and cannot tell us. And this has been made possible by these magnificent detectors that are essentially a new type of observatory that doesn't use telescopes to collect lights, but uses a detector that I will tell you a little bit about to detect gravitational waves. Okay, but what are gravitational waves? How is this amazing feat of detecting them accomplished? And why is this so important? Okay, so let's start with the first question. What are gravitational waves? So if you really want to know what gravitational waves are, you need to take like 3 years of undergrad physics classes, and then a few graduate classes in general relativity, and some math classes in differential geometry and manifolds. But we don't have that kind of time, so I'm going to try and do it in 1 minute. Okay. So over 100 years ago, Einstein came up with a beautiful, elegant, and very accurate theory of what gravity actually is. And that is that you have to think of space not as something that's empty, but as if there were this invisible underlying grid that determines the distance and the geometry between any 2 points. And this grid can be distorted by mass. So if you have mass, it'll actually distort this grid of space, which means it will distort distances and it will distort geometries around that mass. So the moon orbits the Earth, or the Earth orbits the sun, not because it feels a force acting on it, some invisible force at a distance, but just because it thinks it's traveling on the equivalent of a straight line in curved space. And the space is curved by the mass, and that is what dictates how things move in space. Okay, so this is kind of the mental picture you need to have for this. And the theory can be summarized in 2 sentences, which is mass tells space how to curve, and space tells mass how to move. And that very elegant explanation remarkably explains almost everything we know about how things move in the universe. Now, of course, there's some math to it. Okay, so there are, this is all very accurate. There are equations that tell you here like what the mass is and how it tells space how to curve. And then the second part has a bunch more equations of how space tells mass how to move. Now, don't worry, there will not be a test. But I'm just putting this up here to show you that many people think of general relativity in this sense, but it is actually a full-fledged mathematical theory that is very accurate and can predict the motions of planets and stars and galaxies with huge precision. And so far, it has passed every single test that we have given it observationally with flying colors. So we really like this theory. And that was in 1915 when Einstein released it. And a year later, he took the theory one step further and said, well, if mass can cause space to curve, maybe we can get space to wave or to wiggle. And one way to do this is by moving masses around each other. So he imagined if you'd have 2 very, very massive objects that they distort space a lot. If you get them to orbit each other, they could make space wave this way. And that would actually remove energy, and they would get closer together and make space wave more, and then until they merge, and then it would stop. So those are gravitational waves. There are distortions in space itself, in the geometry of space, that propagate outward. So he had predicted this mathematically. It came out of the math of the theory, but he was not very confident that we would ever be able to measure that. But the ability to measure it, actually, it did take a long time. The first measurement happened almost exactly 100 years after he predicted it. And it was due to this wonderful apparatus that was designed by this brilliant person, Albert Michelson, in the late 19th century. He was the first American to win a Nobel Prize in the sciences. And he devised an apparatus which uses light and mirrors in a very clever way, which was instrumental also in the discovery of the special theory of relativity and the general theory of relativity, which is what we're talking about now, this gravity and distortion of space-time. So this machine that you can see him looking through here is called a Michelson interferometer. And let me show you what that is, because it is crucial for our story here. Okay, so here is a Michelson interferometer, and here's how it works. You have a source of light. Okay, imagine a flashlight. It sends light out, and then that light hits a beam splitter, which splits it in half, and half the light goes to one side, and half the light goes in a perpendicular direction. They encounter a mirror, which bounces the light back. It meets up with its other half, and goes into a detector. That's all there is to it. That is the Michelson interferometer. It is as brilliant as it is simple. In fact, this thing is so neat that I actually took one to a bar once. And this is Astronomy on Tap Santa Barbara that Ryan referred to. And we were actually demonstrating how this works in a bar. This happened when the first gravitational waves were detected. Okay, so what is so special about something that splits light in 2 and then brings it back together? Well, nothing much, except that light is a wave, and waves have this wonderful quantity we call interference. So anything that's a wave, if you add to it another wave, and if they're aligned like this, peak in front of peak, they will get stronger. You will get a stronger wave, the peaks get stronger, so they add in a constructive way. But there's another way you can add 2 waves, and that is if you shift one just a little bit, so that they're anti-aligned before you add them together. And now when you add them together, they actually cancel out. So this is what we call constructive and destructive interference. Now, this is a pretty amazing quality of anything that's a wave. So sound, for example, is a wave. And this means that you can take sound plus sound and make silence. This is how noise-canceling headphones work. But it also means you can take light and make darkness out of it if you add them in this very specific way. So you can tune your interferometer to do just that. So here's a fancier view of the light as a wave going through the beam splitter. Here's one of them hitting the mirror, coming back on the other side. And you can tune it so that when it meets up with its friend, they are just shifted in phase, and you get darkness on the other side. So this is how you can make light and light together, make darkness. Okay, what does this have to do with gravitational waves? So when a gravitational wave is moving through space, in 3 dimensions, it kind of looks like this. So one direction of space is squeezed while the other one is stretched, and vice versa. So if I now take my L-shaped Michelson interferometer and I put it here, one arm is going to be squeezed while the other arm is stretched, and vice versa. And they're going to do this in opposite ways. And that is going to change how the light meets at the end. So here is the animation of it. So here's a Michelson interferometer, as usual. And now if a gravitational wave passes through this instrument, it's going to shorten one arm relative to the other, and it's going to change the phase at which these 2 light beams meet. And you are going to get, instead of the darkness that you had before, you're going to get light or darkness depending on the frequency of the wave that is going through your instrument. So this is how gravitational waves are measured. Right? You need this whole sophisticated thing because you can't just stand there with a ruler waiting for a gravitational wave to pass, because both you and the ruler are going to be stretched and squeezed together with space, and you won't notice anything, but light notices. And so this is how to get around that and have this very clever way of detecting that a gravitational wave has passed. Now, there's one catch. Gravity is a very weak force. Okay, you wouldn't think that like if a boulder fell on your head, but in cosmic terms, gravity is a very weak force. And if you take the expected gravitational waves from a kind of merger of these 2 very massive objects, by the time it reaches Earth, it is very, very weak. And the change it will have in one arm of your interferometer compared to the other is this %. Okay, there are many zeros here. So in order to be able to detect that, you need 2 things. You have to have a very accurate instrument, and you have to make it as big as possible so that this percentage is something you can actually measure. Now, for this % to be the diameter of the nucleus of an atom, your interferometer has to be 2.5 miles long on each side. And that is exactly what they built. A giant Michelson interferometer. Each arm is 2.5 miles long. This is exactly the same principle I showed you. The light is coming out of here, getting split into these 2 perpendicular arms, hitting mirrors at the end and coming back. And this is in Louisiana. And so when a gravitational wave passes through Louisiana, it will shrink one arm compared to the other by that percentage, which for this size interferometer is about the size of the nucleus of an atom, and they can measure that. Okay, it is an incredible feat of engineering. It is the most precise instrument ever built, and it took decades to perfect and get better, and they were able to do that. And not only did they build one, they built 2. Here's the other one in Washington State. And the reason you build 2 is because this is such a sensitive measurement. First of all, you want to be sure that you detected something that's real. So if you detect the same thing in both detectors that are several thousand miles apart, you know it's a real thing. And the more important reason is if a gravitational wave crosses Louisiana, it'll take it a few more fractions of a second to get to Washington. The gravitational waves are moving at the speed of light. And that fraction of second difference can tell you where in the universe did this wave come from by the time difference between the 2 detectors. So they're essentially copies of each other. Here's a picture from inside. So this is one of the mirrors at the end of one of those arms. It doesn't look like a mirror. It looks transparent. That's because the laser is an infrared laser, and so the mirror reflects infrared light. But to our visible light, it looks transparent, but that is actually a mirror. And here is the beam splitter that splits, and a very excited LIGO member, that splits the light in 2, and it goes into 2 arms over there. So this is actually an incredibly sensitive instrument. Once they turn it on, they can measure not just gravitational waves, but they're sensitive to all kinds of things. I was in their control room once, and I took this picture of a monitor that's monitoring the ocean waves in both the Pacific and Atlantic Ocean, because just the sloshing of the waves moves the ground enough for them to be able to detect it. And of course, a truck passing by like 10 miles away makes a signal, and they have to know how to clean all that out just so they detect gravitational waves. So in 2015, in September, as soon as they turned it on, actually I think a couple days before they officially turned it on, but it was on because they were trying something, a huge signal passed through the detector, gravitational waves caused by the merger of two black holes. These are the most massive objects in the universe, and this was the first time in history that gravitational waves were detected, and it was a huge deal. So this was announced a few months later, but it happened in September of 2015. This is the first time in the history of humanity that we were capable of detecting this physical phenomenon that was predicted by Einstein 100 years before, and was detected thanks to this amazing feat of engineering. Now, you can see many of the news stories were like gravitational waves detected, vindicating Einstein, astounding discovery was predicted by Einstein's theory of relativity, and Einstein was right, and all these things. We didn't really doubt that. That is not the, it's great that Einstein was right and it works and it was detected. But really what this gave us is a completely new way to study the universe that we had not had until now forever. Especially, in two black holes, one thing everyone knows about them is they're black. They don't emit light. We didn't know black holes were merging in the universe, black holes of these sizes and at this rate that they are now detecting them. And so this is something light could never have told us was happening. So it's like getting another sense on the universe. Until now we could only see it, and now we can maybe feel or hear it through gravitational waves. And this was a huge discovery that won the team the Nobel Prize in Physics in 2017. Now, this is great. And we have light that can tell us everything we've learned so far about the universe. We have gravitational waves that can tell us about these black holes. But black holes don't emit light. And what we really wanted was something that does both. And so we can combine both of these new messengers, light that we've been using for hundreds of years and gravitational waves, the new thing, and study the same phenomenon from both aspects. This is like there's certain things you can see and there are other things you can hear. But if there's something you can both see and hear it at the same time, you can study it and learn much more from it. So for that, black holes are not very useful to us because they don't emit light. So we have to go to the next most massive and dense object we know in the universe, which are neutron stars. Neutron stars are the result of the collapse of a very massive star in on itself. This is a star that weighs about the mass of the sun, or even twice as much as the sun, but it is crushed into the size of a city. So this is what a neutron star would look like if it were over San Francisco. So it is about a few miles wide, but it packs into it the mass of a whole sun. And so a teaspoon of this stuff would weigh like more than Mount Everest. It is very, very dense material. We do not fully understand the physics of what happens to matter when you squish it this densely. In fact, this density is similar to the density inside the nucleus of an atom. So you can think of neutron stars as city-sized stars or city-sized atoms. Either way, they're pretty astounding objects. And if they happen to be in pairs and they happen to be orbiting each other, this material is so dense it will also create gravitational waves. But the difference between this and black holes is very big. And so here's a simulation of two neutron stars merging together. And one big difference that doesn't happen in black holes is that stuff can escape. Material is flung out. And this material is very hot and is very rich with neutrons. This is why they're called neutron stars. And when very neutron-rich and hot material gets expelled like this, these are perfect conditions for creating the heaviest elements in the universe. So very, very hot neutrons are slamming into other neutrons and slamming into atoms. And in a very rapid process, they make the heaviest elements in the table of the elements. And this is one of the only places in the universe that people have thought, maybe that's where the elements come from. Even in the Big Bang, the conditions were not this extreme to allow these elements to be created, and yet we know they exist today. So somewhere they must happen, they must be created, and for many decades the theory was, well, it must happen in neutron star mergers. Now when these elements are created, they produce a flash of light that can last a few hours or a few days, and that is what we wanted to detect. So just finding that flash of light randomly on the sky is very, very difficult. But now that we have this new tool of gravitational waves, they can tell us when this happens and where, and then we point our telescopes and look for that flash of light, and then we can get both of these messengers and learn all of the physics related to these events. So the expectation was, okay, here's an illustration of a neutron star merger. You get the neutron stars themselves merging there in the center. Because they're so dense and so heavy, they distort space-time in a way that produces these waves, these gravitational waves. And the material that is flung out is so hot that you have all these neutrons being squeezed into atoms, making the heavy elements and producing a flash of light that we call a kilonova. The reason is there's a completely different astronomical phenomenon called a nova, and this was predicted to be 1,000 times brighter than that, and so it got the name kilonova. And it kind of stuck. Now there's another thing in this illustration which I have not yet mentioned, and it's this jet of material that is flying out from the center of the merger. And this was also a theoretical prediction. It was that you'd have this very, very fast material moving at, like, thrown out at almost the speed of light, and it is so energetic that it shines in the most energetic form of light we call gamma rays. And if you happen to be at the other end of that, so if that thing is pointed toward you, you will see a flash of gamma rays. And we have seen flashes of gamma rays, but we didn't know if they really, that's what the story was, if they were really coming from merging neutron stars. And if you're looking from the side, you're not supposed to see anything. So there's only a really small chance, if you're really lucky and you happen to be in the direction of where this jet is flying, that you will see the gamma rays. But otherwise, you're expected to see the gravitational waves and the kilonova, which is this other form of light from the creation of the heavy elements. Okay, so the plan was we wait for gravitational waves, and then they tell us, okay, we just got gravitational waves from 2 neutron star mergings somewhere in that direction of the sky, and now we point our telescopes and we look for the kilonova. There's only one catch. The area in the sky in which the gravitational wave detectors can tell us the signal came is usually pretty big. So here's the first detection of gravitational waves of those 2 merging black holes in 2015 on top of a map of the sky. And this is their localization. It is kind of somewhere in that banana-shaped part of the sky. So this is the detector's way, LIGO's way of telling us it happened somewhere here, probably. Okay. And so now we have to figure out where exactly and find this fleeting flash of light that is going to disappear in a few days. Okay, so you're a scientist and you want to get in on this. And so you think, okay, here's what the theorists, the people who do the models, tell us that this light should look like. It's going to be faint, relatively. It's going to be very red light, even infrared light. And it's going to be somewhere in a large part of the sky that they can't tell us any better than that where to look. So you think, okay, as a prudent scientist, what I need to do this is a large telescope. I need an infrared camera attached to that telescope, and I need it to have a wide field of view so I can cover that whole banana on the sky very quickly before the thing disappears and find it. Okay, so as a postdoc in Santa Barbara, I thought to myself, well, what do I have? I have small telescopes with visible cameras that cover a tiny fraction of the sky. Okay, but we decided to do it anyway, and I was kind of surprised when they said, sure, you can, your proposal to search for counterparts of gravitational wave has been granted time. Okay, it was not obvious to me that that would happen because, it wasn't exactly the ideal experiment you would design, but you do what you have with the tools that you have. One thing we did have with these telescopes that no one else had is a worldwide network of them. So the place I did my postdoctoral work in Santa Barbara is headquarters to the Las Cumbres Global Network of Telescopes, which currently has 22 telescopes around the world, and they are all fully robotic. There are no people at these telescopes. They are run completely by software and robots and computers, and you just tell it, I need to get an observation of that part of the sky at this time, and it figures out which telescope has the good weather and when it's nighttime and where to send it to. So this is a completely new tool in astronomy that we did not have before. And we figured, well, maybe we can use this to tackle this challenge. Okay, how do we get over the problem that, here's another map of the sky, and here's an actual localization that LIGO gave for an event, it's somewhere in this weird shape, and that is our field of view. We cannot cover that whole shape. It would take months, and the thing will be gone within days. So how do we get over that? Well, you don't actually have to search the whole region, because the neutron star merger, if it's somewhere in here, it's not just going to be in a random part of the sky. It's probably going to be in a galaxy. Most stars and mass in the universe is concentrated in galaxies. So if we know where the galaxies are, all we really have to do is just hit the galaxies, and we don't really care about the space in between the galaxies, because the chance of it happening there is much lower. Okay, so this doesn't guarantee that we'll find it, but it does save us a lot of work and increase the chances dramatically. And so we wrote an algorithm that would listen for alerts from the gravitational wave detectors. They would send us an alert. We would pick it up. We wrote an algorithm that would prioritize what is the most likely galaxy that it's in and where we should search, and it just sends it to the telescopes robotically and starts getting data. So we did, this could have happened without any human intervention, but we weren't that sure of what we were doing, so we made a web page where it would tell us, okay, we got this alert. This is the actual one from August 17. Here's the galaxies I think you should look at. The list goes down further. You scroll down. These are the top 5. And, I just let me get these observations. And then we just click the big green button, and everything else happens on its own. Okay, so that was the plan. Here's what actually happened. So on August 17, 2017, the gravitational waves generated by 2 merging neutron stars reached Earth. Now, if you look at how these waves behave, you see they're getting stronger and stronger and faster as the neutron stars merge, and then they stop. So this is the kind of characteristic signal they're looking for in the gravitational wave detectors. They're looking for something that has a certain frequency, and the frequency of the waves is going up, and the strength of the waves is going up, and then it gets very, very high, and then they merge, and then you get nothing. Here's what they saw. So this is a plot of frequency as a function of time. So all of this background is noise, but you see the signal right there, getting higher and higher frequency and stronger, and that's when the neutron stars merge. So this is what it looks like on the LIGO side of how they saw it from one detector, the one in Hanford, Washington. The one in Louisiana saw a similar thing. You see it right here. The frequency is going up and up and up until they merge. But it had this ugly thing on top of it, which is what they call a glitch. It is a malfunction of the detector that they don't exactly know what causes it. But it lasts less than a second. So they weren't too worried about it because what are the chances that something that lasts less than a second and happens once in a while will happen right on top of the first neutron star merger? Okay, it's 100%. That is the chance. And so what this caused was that we only, the automated software that they made to figure this out and find these events said, well, I'm not dealing with that. Like, that is off. I don't know what to do with this. So you only get one detector, and if you only get one detector, you don't get a position on the sky. So we couldn't figure out where it was until they cleaned this up and then gave us the position. But that was going to take a few hours. Now, so we didn't expect that to happen. So we couldn't do anything. But then the other thing we didn't expect to happen was that the NASA Fermi satellite, which was up in space looking for gamma rays, happened to detect a burst of gamma rays at almost exactly the same time that the LIGO detector detected the gravitational waves. So here's what it looked like together. You have the LIGO detector at the bottom detecting gravitational waves. At the same time, here's the readings from the satellite, the NASA satellite that detects gamma rays. And you see here they spiraling in. The merger happens, and 2 seconds later, there's a burst of gamma radiation, which we also didn't expect, because I told you had to be, like, the jet had to be pointed at you for you to see that. And we didn't think we would get that lucky on the first time. And apparently either we did or we don't understand how well, very well how the jet works. And so this actually was like 100 times weaker than what we thought it was if we were in the jet. But it is, it exists, and we didn't think it would exist if we were off axis from the jet. So that was a surprise. And actually, you'll notice, by the way, the frequency of the gravitational waves, the frequency at which space itself is vibrating, is around 100 to 300 hertz, which is the frequency you can hear. So if gravitational waves were sound waves at the same frequency, here's what it would sound like. Let's see if we can get this going. This is the actual frequency of the gravitational waves from neutron stars emerging. And that's the gamma rays, which apparently sound like a bell chime. Okay, so then we expected we would have 2 LIGO detectors that would give us a direction. Instead, we had one that wasn't working, but they were working on getting it cleaned up, and this unexpected luck of having the gamma rays as well. So here's the actual circular that was sent. This is the astronomical equivalent of a bat signal, where people announce things rapidly to other astronomers. And this is by the Fermi team, and they said the onboard trigger time of the Fermi, the satellite, is approximately 2 seconds after the LIGO trigger, the single interferometer LIGO trigger. Now, it's still, one of the things we're actually discussing at this workshop is why 2 seconds? Why was the gamma ray delayed 2 seconds compared to the gravitational waves? And there are many theories about that, but we're still actually not sure. But the chance that it would happen 2 seconds after and not be related is a fraction of a percent. It is actually, let me get you the numbers here. It is 5 millionths of a percent is the chance that these 2 things are not related to each other. Okay, so they very likely are related, and we have to figure out why there was this 2-second delay. But the nice thing was that the Fermi satellite can give its own direction on the sky from where the gamma rays came from. Okay, so if we believe they came from the neutron star merger, Fermi was telling us, okay, while they're working on the other gravitational wave detector, this is where you need to look. There's a map of the sky. Here's the Milky Way. And this is an area where they say, okay, we kind of think it's in here, but it might be also in here, and we're pretty sure it's at least somewhere in this big circle. Okay, so we got our localization. So that is an illustration of what it looked like, and this is an illustration of our reaction, because we were not set up to follow, our whole sophisticated automated thing to figure out the galaxies assumed we would get a localization from the gravitational waves, not from the satellite. Okay, what's the difference, you ask? Well, of course, they deliver them in a completely different format that we had no idea how to read. So we really were starting changing our code in real time so that we can read this localization, and we started searching for galaxies in the most probable region here in the center. Okay, and then as the hours went on, the LIGO people were able to fix that glitch that happened. So here is their actual circular investigation of the Louisiana Livingston data, identified a noise transient known as a glitch during the in-spiral signal, and they were able to clean it out, and an updated sky map is now available from all 3 gravitational wave observatories. Why 3? Because there's the LIGO one that didn't have the glitch, the Louisiana one that they fixed the glitch, and the third one was another interferometer in Italy called Virgo, which was turned on 2 weeks before for the first time at those sensitivities. And so it is not as sensitive as the LIGO ones. The arms are shorter. They're not quite 2.5 miles long. They're shorter, so it's less sensitive, but it was able to contribute to the localization of this event by having 3 detectors on Earth, 2 in the US, 1 in Italy, and that gave a much smaller region of the sky than what we thought. By the way, this sky map, the thing that actually calculates the map on the sky, was written by Leo Zinger, who's a participant in the workshop here. And thanks to him, we have this ability to just know where to point our telescopes. So here's the localization we had before. And now that the gravitational wave detectors cleaned out all the glitches and collected the information from all 3 of them, they said, okay, that's where you need to look. That's where the gravitational waves came from. So it overlaps where the gamma rays came from. Okay, so that is an illustration of where we should look. And here is an illustration of our reaction, because by the time we figured this out, we were searching here. And now it says, no, you need to search in this area. Okay, so we had to tell our telescopes, okay, stop whatever you're doing, and here's a new list of galaxies for you. So luckily, our telescopes are obedient for now. We don't know what will happen. But here, we started to observe the new list of galaxies once we finally had this correct localization to look at. And so here is a zoom in of that area, and here's where all the galaxies are. This is the full moon just for scale, so you realize how big of a part of the sky this is. And the 5th galaxy on the list was a galaxy called NGC 4993, this one right here. And that's a picture of the galaxy. This fuzzy ball is that galaxy, 130 million light years away. These are stars in our galaxy in the foreground, but that little blue point of light right there is not a star in our galaxy. That is the flash caused by the merger of two neutron stars. That is exactly what we were looking for. And we knew that because it didn't appear in a picture of the galaxy taken before. This galaxy was imaged a few years before as part of a survey of the sky. And this is when we got it right after the neutron star merger, and that flash of light was not there before. Now, we were very excited, but it turns out there were 5 other teams that were doing the exact same thing, or reached the exact same conclusion, but with completely different telescopes and different techniques and different strategies. Some of them had their own galaxy list. Some of them were just tiling the whole region and looking for something. And you can see here, this is 10.8 hours after the merger, and 11.57 is when we got our image. So we, all 6 of us, independently narrowed in on this one galaxy within 45 minutes of each other. So these were different teams around the world. We were the one that was over there. And the first ones was the UC Santa Cruz team, led by Ryan Foley himself, who is organizing the workshop here and who introduced me. And so his team was the first to find it. And actually, the person looking at the data was a postdoc working with Ryan, Charlie Kilpatrick, who's sitting right there in the back. So Charlie is actually the first human being in history to see an image of a kilonova. So they sent out their alert. So it was written by a graduate student in Ryan's group, Dave Coulter. So here's Charlie, here's Ryan, their collaborators. Potential optical counterpart discovered. Okay, and once they sent that, the circular started flying. We're like, oh yeah, we saw that too. What did you see? Or ours looks like this. We saw it in this galaxy. Yeah, we're all looking at the same galaxy. And now everyone started getting in on the action. That's the NASA Swift satellite, whose director, Brad Senko, is also here, part of the organizing the program. The NASA Hubble Space Telescope, of course, our best telescope, was pointed at it. And in fact, almost every single telescope on the planet, in every continent, including Antarctica, someone pointed a telescope at Antarctica to this thing, was following this event and looking at it. Every telescope on the planet and pretty much every telescope off the planet as well. There was just one catch, which was this happened in a part of the sky that was only visible for 1 or 1.5 hours before it went below the horizon, and you had to wait for the next night to see it again. So all these telescopes in Chile that discovered it could not look at it again until 24 hours later when it appeared again over Chile. So this was quite a limitation because we knew this thing was going to change very rapidly and we didn't want to miss anything before it would disappear. So I'm going to let my colleague and postdoc advisor, Andy Howell from Santa Barbara, explain what we did.
Getting around that limitation is exactly why we built Las Cumbres Observatory. It's a robotic network of telescopes placed all around the globe so that there are always telescopes in the dark. These icons represent where we have telescopes. When we first discovered the explosion, it was over Chile. But then, as the Earth rotated, we picked it up again over Australia. And then, 8 hours later, we saw it over South Africa. In the 24 hours that the Earth takes to rotate, we can observe the explosion 3 times with our network.
So these dinky little telescopes that we had, actually not only were they able to see this event, which turned out to be brighter than expected and not as red as expected, and in a smaller part of the sky than expected, which was exactly what we needed. In addition, we were able to observe it 3 times per night from our 3 different sites that could see this. So we didn't have to wait 24 hours. We could see it once every 8 hours. So what did we see? Well, here is the brightness. So what we can measure when we take images of these things are their brightness and color, basically. But there's a lot of physics we can learn from that. So here's the brightness in millions of suns. So it is bright, but it's very far. In the first 4 days of this event. So first, that was when it was discovered by the different teams over using telescopes in Chile. It was about 150 million times brighter than the sun, intrinsically, if you were there. That's how bright it would be. And it was quite blue, which was kind of surprising to us. And we're still trying to figure out why. Then, when we observed it over Australia, it got brighter. And by the time we could observe it over South Africa, it got much fainter. And then we kept observing it through our observatories around the world. And we could see it change. We had never seen anything this bright change this fast in brightness and color before. But you can see that if we had only had one telescope, we could have only observed it once every 24 hours. We'd have missed what was going on in between. And this, how bright it got at peak and when that happened is a key to a lot of physics. And if we would have missed that, we could not have known all that physics. So that was our contribution to this. And there were many, many other contributions that came out in this. One of the papers, there were about 80 papers about this event that came out on the first wave. Since then, there's been, I think, 1,000. We're probably around there now. But this was like the one paper where everyone got together, the LIGO people, all the different astronomy groups that were competing with each other. There's about 3,500 authors on this paper, we think, because we don't exactly know. But here you can see the whole story, from the gravitational waves right up there at the beginning, the gamma rays that came as 2 seconds later, and then these 6 discovery image of the light, the optical light that was seen in this galaxy a few hours later, and then a few days later it was detected in X-rays and radio waves as well. So we had the complete electromagnetic spectrum in addition to the gravitational waves. Now, another part of this story is that we were supposed to keep all of this a secret for 2 months. Our agreement with the gravitational wave detector people, they said, okay, we'll let you know when a neutron star merger happens, but you can't tell anyone until we say it's okay. Because they wanted to be the ones to make the announcement, because they worked for 40 years to make this possible, and they didn't want some group of 10 astronomers scooping them on this discovery, which makes complete sense. And so we all agreed to that, and we actually signed agreements with them. Okay, we will, we're vowed to secrecy until you tell us it's okay. So there were 2 months where they had said, okay, you cannot talk about this, you can work on your data, and then after 2 months you can all release your papers at the same time. Okay, but we were so excited about this that we could not contain ourselves. So 2 days after this happened, right, one day, it's August 18th, so Craig Wheeler, who's an astronomer at the University of Austin in Texas, new LIGO source with optical counterpart, blow your socks off. Okay, he was here at the conference as well. He was then reprimanded by LIGO and he took the tweet out. And they thought, okay, no one saw that tweet. Craig's a great astronomer, but maybe doesn't have that many Twitter followers, so we're good. Except when someone triggered the Hubble Space Telescope, there's a website you can go. Hubble Space Telescope is like government facility. It's run by NASA. Everything it does is public. You can go into this website and see what is the telescope looking at. But of course, no one knew about this website. No one actually was following Hubble, except that the summer before there was an intern working at the Space Telescope Science Institute, which is what operates Hubble, and their job was to make a Twitter bot that tweeted everything Hubble was doing, called Space Telescope Live. And that actually had a number of followers. And so when the telescope was triggered, this tweet came out. I am looking at the star binary neutron star merger with Space Telescope. Here's where it is on the sky. So Matt Nichols, a friend of ours, who's the one who triggered the telescope, and when you trigger it, there's a form you have to fill out, and you have to give a name for your target. So he didn't think this would end up on Twitter, and he just called it binary neutron star merger, right? It's pretty obvious what it is, and that ended up being tweeted. And again, it's this frenzy, take this tweet down before anyone sees it. Okay, but it was too late. The press had picked up on it. So we may have detected a new kind of gravitational wave. Rumors swell over new kind of gravitational wave sighting. Gossip over potential detection of colliding neutron stars has astronomers in a fizzy. Okay, and then if that weren't enough, all of these circulars, these bat signals we were sending each other with all the information and all the data and everything that we were finding were supposed to be private, but there was an accident that made these things publicly available for a period of 2 hours online. Okay, so if you happen to have been searching these things, you would have known all the secrets ahead of time. And then they quickly fixed that, but then like a day before the announcement was officially made, this thing called the transient name server sent out this email, oh, there's this new thing in the sky, and the classification of it is Kilonova. And this was released 24 hours ahead of when it was supposed to release. So my point here is, if you think astronomers can keep a secret, you are extremely wrong. And so this proves to me that there's at least, we cannot keep a secret, let alone maintain a conspiracy. Okay, all the people who think they're aliens and we're hiding it, this is how we could not hide a neutron star merger. Okay, but what did we learn from this? So from the light that came out of this merger, we were able to analyze it. And the color changes and the intensity of the light tell us a lot about the physical processes that were going in there. And it indeed confirmed that the heaviest elements in the periodic table are formed by merging neutron stars. This is how much of these elements are formed based on that one event. And so you can see that most of the high numbers in the table are formed by merging neutron stars. Everything else, we kind of think we know how it's formed, the first few in the Big Bang and then in exploding stars and other processes. But we were missing where all of these elements come from. And now this flash of light that lasted a few days confirmed that that is where the heavy elements come from. So you'll notice here's gold, number 79, and right above it, silver. So if you have any silver or gold jewelry, and if you could ask those atoms in that piece of jewelry where they came from, they would tell you they came from the merger of two neutron stars. This we know now as a scientific fact. Okay, so of course, everyone was excited about the gold. That is where gold is made. So how much gold was actually made in this merger? So we don't really know, but there are some estimates based on how much light came out that it produced about 100 Earth masses of gold. Which is a lot. So of course people, were tempted to do the next step of calculating, well, how much is that worth? So it turns out if you take the price of gold back, at 2 years ago, the amount of 100 masses of Earth is worth $25 million dollars. And even the Business Insider even made a story about this. They got a number slightly different. I think they're wrong, but okay. There's enough zeros in there. That is what the amount of gold is worth that was made in that merger. Now, I am not a commodities expert or an economist, but I think, from my limited understanding of demand and supply, that if we actually had 100 Earth masses of gold, it would be worth exactly zero. Okay, so this taught us a lot about how the elements are created and what goes on at these neutron stars that are, nuclear, these giant nuclei that we didn't know the physics of very well. But we also learned things on a completely different scale. And that is the scale of the universe as a whole. One new thing we were able to do with this event is measure something called the Hubble constant. The Hubble constant is a number that quantifies how fast the universe is expanding. So the universe as a whole is expanding. Everything is moving away from everything else. And we want to know how fast that is happening, because that helps us understand the physics of why it's doing that. And so there are this number, the Hubble constant, is around 70. In these units, but there are two main ways of measuring this number until now. One is this thing called Planck, and it gave a number and an uncertainty that was just under 70. And the other method that's independent of it uses exploding stars and a bunch of other things, gave a number that's slightly over 70. And the uncertainties don't overlap. So this is a problem, because these are two methods that are supposed to be measuring the same number. So why are they different? Either one of them is wrong, or there's physics we don't understand. Okay, that's what gets us really excited. So this is a third method that could help us determine what is going on. And that is because the strength of the gravitational waves can be used to infer how far away they came from. So the gravitational waves, when they come here, they tell us what distance they traveled. And if we can find the flash of light and know what galaxy it's in, we can measure how the universe is expanding between us and that galaxy. And if we can combine those two things together, we can get the Hubble constant, how fast the universe is expanding at a certain distance. And so what we got was a number that, the most certain value is right in between these two other estimates with an uncertainty that kind of covers both of them. So it doesn't really tell us who won just yet, but it is a demonstration of a completely new method, totally independent of the other two, that can measure this number. And once we have enough of these events, this uncertainty is going to shrink, and we're going to know if it zeroes in on this value or a third value. So this is another thing that we hope to learn from these kinds of events. So this one flash of light that lasted a few days taught us where gold and other heavy elements in the universe are made. It taught us about how matter behaves at these atomic densities that are in neutron stars that are huge, or it started teaching us about these things. It confirmed the connection between these gamma rays that we were seeing and didn't really know they were coming from merging neutron stars until now. I mean, that was the theory, but there was no confirmation. And all the way up to the biggest scales we know of the expansion of the universe as a whole from this one event. But it also opened up a bunch of new questions. So here are all the known neutron stars and black holes, and this is their masses in solar mass units. So most neutron stars, or all neutron stars, are between 1 and 2 times the mass of the sun. All black holes we know are 5 and above. There's this gap that we don't understand. And this merger took 2 neutron stars from here and merged them together to a total mass that is right in this gap. It is either the most massive neutron star or the least massive black hole. We don't actually know what determines, if you're a neutron star or a black hole and where that line passes, and this thing is kind of right in the middle there. So we don't know if it turned into a black hole or a neutron star, but there are many people working on trying to figure this out from the data, and if so, that can tell us where the limit actually is, and that teaches us a lot of physics as well. So many open questions from this event, which are as interesting as what we learned. Why was it so bright and blue, and we were told it was going to be faint and red? Why was the gamma ray associated with it so faint? How common are these things, right? Think about it. The light and gravitational waves from these events were traveling for 130 million years until they arrived on Earth. If they would have arrived 2 weeks earlier, the Italian detector would have been offline. If they would have arrived 1 week later, all detectors were offline. They were scheduled to turn off at the end of August in order to do more maintenance and upgrade them. So, this 130 million year journey landed in the exact 3-week window that we needed it to land in order for us to detect it. So either we were extremely lucky, or these things are more common than we thought. And with one event, we don't know yet, but that's what we're waiting for more. And of course, what did this merger make? Did it make a very massive neutron star or a black hole, a very low mass black hole? So what's next? Well, that was the first event. The gravitational wave detectors are always improving their sensitivity so they can find more of these. They actually turned on again last April with unprecedented sensitivity, and we have all been at the edge of our seats since then. Literally, we get alerts to our phone when these events happen so that we can trigger our telescopes immediately and find the next one. So we're waiting for the next events. They're finding now merging black holes about once a week. This is something that had never been detected until 2015, won the Nobel Prize, and now it's happening once a week. Merging neutron stars are less common than that, but we had one in April, and we almost had one last week, but it turned out to be a glitch in the detector. But it was an hour-and-a-half period where we were all scrambling to try and observe it. More countries are building gravitational wave detectors. So in addition to the ones in the US and Italy, Japan and India are going to join this club. That is one of the arms of the detector in Japan, which is underground. It's actually going to turn on at the end of this year for its first run. And we're sending gravitational wave detectors to space. So there's going to be an array of satellites doing this kind of interferometer between them in space, but like millions of miles apart. And what that allows us to do is detect gravitational waves at frequencies that we cannot detect from Earth, because the Earth is always vibrating at some level. Even when there isn't an earthquake, there's always some vibration, and that sets a limit on how sensitive the detectors can be if they're on Earth. They just cannot get rid of those vibrations. So if there's a gravitational wave at the same frequency that the Earth is vibrating, they're totally blind to that. But you're not in space. So you could see gravitational waves at totally other frequencies, and these are totally other physical phenomena that are generating them, and many of them we don't even know what it's going to be. It'll likely surprise us that we will be able to detect. So this is really a new era in astronomy. We cannot overstate that. It is really something that is equivalent to the invention of the telescope 400 years ago, and we are living it right now. And so that's why we gathered here in Aspen to have this conference of astrophysics in the LIGO and Virgo era. That's the name of the detector. And there are people here who work on, like Ryan and Charlie and me, who work on telescopes to try and find these flares. There are people who built the LIGO detectors and understand them and know how to interpret their results. There are people who work on the models and the theory behind all of this. There are nuclear physicists. There are black hole specialists. And we're all here together working very hard to figure out what more can we learn and how to exploit this revolution really well. And sometimes we work a little less hard on that. This is just part of the group, but I just want to say how wonderful it's been to spend time here in Aspen and working, but also enjoying the beautiful surroundings here, which are very inspiring and very conducive to creativity and to collaboration. And so I want to thank everyone who really has made us feel at home here in Aspen, and the hospitality we've gotten has been great. And thank you very much for coming.
Thank you so much, Iair. That was fantastic. So we have time for questions. As you can already tell, Iair is incredibly smart, Einstein level. But I also wanted to point out something that recently, Iair was part of this competition for research money where he had to fly to Brussels and give a 10-minute presentation, and then he was questioned by a bunch of scientists. At the end of it, he got 2 million euros.
Not to my bank account.
Yeah.
For research.
So he survived that questioning period. Now let's see how well you guys can do. Because you guys are not mic'd, Iair's going to repeat your question so that people on the video feed can hear you. So we'll start over here on the right.
I understand that there's been a detection of a neutron star being disrupted by a black hole. Has that been confirmed? And
Yes.
what have we learned about it?
Thank you very much. Yeah, so the question was there a detection of a neutron star merging with a black hole? Yes, I told you the first gravitational wave was black hole merging with a black hole. The one we got very excited about, neutron star with neutron star. What about neutron star with black hole? And that happened for the first time 2 weeks ago. Was detected by the LIGO detectors, a neutron star and a black hole. We, of course, all turned our telescopes to look for the flare, and we have not found it yet, but hope is not lost. We don't know, actually, if there is supposed to be a flare from this kind of event or not. So we looked, and so far there's been nothing, but people keep looking, and like every day there's like, oh, maybe it's that thing, and then we get more data on it, and oh, it turns out that's not related. Maybe it's that thing. So we've been spending the last 2 weeks doing that. Yeah, and I'm allowed to tell you this because since the gravitational wave detectors turned on again in April with their new sensitivity, they decided, okay, no, they'll be less secretive. All of the alerts are public, so you can sign up if you want to get gravitational wave alerts on your phone. And this is all public information, so they tell us, that now we don't have to worry about, they saw how bad we were at keeping secrets, so we don't have to worry about that. And we can tell you about this. They don't give us all the details of the event, because they still want to save something for their own publications. But it's enough for us to know, should we be searching with our telescopes or not. So 2 weeks ago was the first neutron star black hole merger, but still no optical counterpart.
Okay, why don't we start in the front row? And I don't know if there are younger people in the audience, but I'll encourage anybody, say, who has not yet graduated high school to ask questions as well. Go ahead.
A couple years ago, I asked one of the people who was doing astrophysicists that was doing the black hole mergers, if they had found any associated gamma rays with that, and they said they had not. And so now this is something else that shows that there is an association with gamma rays or electromagnetic spectral emission. And so now my question is, did you guys see anything like in a way of like neutrinos that were associated with this? Because one of the things at least I've noticed in my kooky news feeds that I get, there seems to be an association with very high energy gamma rays with the emission of neutrinos arriving before the gamma rays, and which would make sense, and also the fact that the gravitational waves would not be impeded the way that photons would be traveling through matter, which is why I think the gamma rays would be delayed. So,
Okay.
have you guys seen any neutrinos?
Okay, so the question, I'll summarize the question of whether we've seen neutrinos come with any of these events, and what about the black hole mergers. So I should say, the black hole mergers are not predicted to produce any light. So most of us, whenever, once a week when there's this black hole merger, we don't point our telescopes at it. But if there's something that, observers like Ryan and I really like, is to prove the theory is strong. And so we are hoping, we have not yet seen any gamma rays or any type of light from the merger of two black holes. But we also had discussions here at the workshop. Maybe there are ways that those events could still produce light. And so we're looking for that as well. And then neutrinos, as you mentioned, so neutrinos are tiny little particles that can go through matter as if it wasn't there. That is a third messenger that the universe might give us. So we have light, we have gravitational waves, and neutrinos is a totally independent thing. And as you say, it can, it just goes out through matter. And so it can tell us what's happening in the cores of stars, in the centers of these mergers. And actually, neutron star mergers produce a ton of neutrinos. However, detecting them is very hard. It is very challenging. And so we have few neutrino detectors on Earth. One of them uses a cubic kilometer of the Antarctic ice as its detector, because maybe one in I don't know how many trillion of neutrinos will actually get stopped or interact with that ice and we can detect it. But they are still only sensitive to events that happen really nearby. So even though neutron star mergers produce a lot of neutrinos, since they're happening in other galaxies, the instruments are not sensitive enough to detect that, we think. Still, every time there's a merger, they look, did they detect any neutrinos? And so far there has been none. And we really only expect that if one of these mergers happens or if a star collapses in a supernova in our own galaxy. If we get that lucky, we will get neutrinos, light, and gravitational waves. So 3 different senses on the same thing. And that would be a huge, huge party. But supernova, or these things happen, well, we don't really know, but once every few thousand or tens of thousands or even more years per galaxy. So we'd have to be extremely lucky to have one in our own galaxy. But, we're ready for it if it happens.
When you compare the timing of gravitational waves with optical waves, what do you assume, and gamma rays for that matter, what do you assume? Do you take the velocity of all of these at a C in vacuum, or do you allow for the equivalent of optical dispersion?
Okay, so yeah, the question was, what about the velocity of the light and the gravitational waves? Is it the speed of light in vacuum? Is there some dispersion? So the Einstein's theory predicts that gravitational waves should move at the speed of light, ideally. And again, this was confirmed by this event, because even that 2-second delay, actually a 1.7-second delay between the gamma rays and the gravitational waves, is enough, because they were traveling for 130 million years, to tell you that their speed is the speed of light up to like 0.01%. And we think actually that 1.7 seconds delay is not due to the travel time, but it's due to how the gamma rays are generated. That there is some delay between the mergers and the gamma rays breaking out that caused that 1.7 second delay. But once they were out, they were trailing each other exactly the same until they reached Earth. So there is some dispersion, but I think it's pretty low and negligible, and it's really almost exactly the speed of light to our accuracy, to how accurate we can measure it.
You mentioned that the physics of neutron stars is not totally understood. What kinds of things might you learn about neutron stars with the kind of observations that you're making?
Well, we just had a session about that this afternoon, so I can now answer this question. So one of the things is we don't know how matter behaves at these insane densities. And one of the ways we quantify that is we say, given a certain density, what's the pressure there? If we can figure that out, that means we understand the physics. And so we don't know that. But if the pressure, you can imagine, if the pressure is big, the star will be smaller. And if the pressure is not as big, the star might be a little bit bigger. Like it might be 10 kilometers across or 12 kilometers across, depending on what the physics is inside. Now, the nice thing about these mergers is that the gravitational waves can tell us what was the mass of each neutron star that merged, and the light, and also the gravitational waves and the light can tell us what was the size of these objects. So it is very hard to measure the size of a neutron star just sitting there on its own. In fact, it's impossible. And when we have two of them merge, we can suddenly get the masses and the radii and the sizes. And those together can constrain what has to be the pressure in each one of them and can tell us, what is the physics going on in there. So that is one aspect of it. And the other is the creation of these heavy elements also depends on a lot of nuclear physics that we're not entirely sure about. So if we can figure out how much of each heavy element was made and how exactly they were made, that can teach us about those processes as well.
So I read when two neutron stars collide, they create a magnetar.
So a magnetar is another name for a neutron star that is one neutron star that's spinning very fast and has a very strong magnetic field. So you can get that when you create the neutron star. It can be a magnetar. And it can create a magnetic field, and that can do all kinds of things, but then it pretty quickly will spin down and kind of become, a less extreme, it slows down its spin, and we think there is some delay by the time you create the neutron star and the time it gets close enough to another neutron star to merge, that by the time they merge, I don't think one of them could be a magnetar, but that might be another layer of complexity that we might have to deal with. Yeah.
Final questions? There are some physicists in the room if you want to throw Iair a really hard question. Okay.
Thank you.
Let's thank Iair.
Thank you.